All right, thanks for all of you who still come back. Some of you have heard parts of this lecture. I will not assume that you have, and we've made progress, and that's what I want to describe here, but I want to set it up completely generally and make it as a general audience lecture of interest to everybody, I hope. The problems are very basic, they're very difficult. Most of this work is recent work with Amit Ghosh, and I will report also a little bit on some work that was done earlier with Bergan and Gumbard, and there are other people whose work I'll mention as I go along. All right, let me stand where I can see this. So I'll be interested in the problem of solving in integers a Diophantine equation of a simple type, which is a polynomial in several variables with integer coefficients equals a number. So let's fix such a polynomial, integer coefficients. I will assume throughout that f is irreducible, absolutely irreducible, and even f minus k is absolutely irreducible, for the reason that we'll be looking not just at f equals a fixed k, which would be the main interest, but we'll allow k to vary because in many problems, like which numbers are sum of 3 cubes or which numbers are sum of 3 squares, that would be the setup. We can also go from the integers to a number field, and by and large, that's something you always want to do. Sometimes that's a difficult and much more difficult situation. Sometimes it isn't, and I will highlight that as well. So throughout, I'll let VKF or VFK be the level sets, which are just affine hypersurfaces. And if we want to find an x, which is an integer solving it, so let's just start with the whole numbers themselves, then there's clearly a necessary condition, which is the standard necessary condition. That is, if you can solve it over the integers, you can solve it modulo q for every q. So that's if you can't solve it mod q, that's a local obstruction, and throughout, we'll be assuming that we are not facing this local obstruction. Now, you might wonder whether checking f of x congruent to k modulo q is something that itself is very difficult to check, because I need it for all q. But for the polynomials, for the f's that we're looking at, which will be degree in more than three variables, as you'll see in the interesting cases, you only have to check this for finitely many q's. So that the local conditions, or finitely many primes, and then numbers which involve, so the local obstruction, if it will exist in anything that I'm looking at, will be simply a condition on q on an arithmetic progression. All right, so let's just sober up a little bit and start with a linear equation. So suppose I want to solve a linear equation, a1x1 plus a1xn equals k over the integers. Well, clearly then the greatest common factor of the a's had better divide k. And if it does, you take that out, and then these numbers are relatively prime, and then you can always solve it. So with a linear equation, there's no issue. We have this very nice situation that if you can solve it locally, you can solve it globally. It's very rare that you'll be in a situation where you can go from local to global so easily, and that's what we're looking for here, such situations. Perhaps the most studied case is that of a quadratic equation. This was Hilbert's 11th problem. It's not usually advertised as clearly as Hilbert phrased it. Hilbert broke its problem into two parts. So you want to solve f of x equals k, where x and k are rational numbers in a number field. So over the rationals, if you just want to stick to the rational numbers. But he specifically asked over a number field because he'd understood that some work that he had done in particular might be relevant for this. In particular, some beginnings of class field theory. And the more difficult question that he asked, following works of Minkowski and Smith, was how about local to global principles where x and k are to be integers in a number field? So I want to emphasize that the integer case is much more difficult than the rational case. And the famous Hasse-Minkowski theorem solves this problem over the rational. So Hasse completely resolved this Hilbert 11th problem in the easy first half, and it's as good as it could be, and it's the theorem that I think we love in terms of local to global principles and have looked to generalize it, so much so that if a variety has this property, we say it satisfies a Hasse principle. And that's the theorem that you can solve the equation f of x equals k, little k, over a field capital K, over a number field K. But as I say, you can stick to Q. That is, in fact, Minkowski's case. If and only if you can solve it locally over every localization of the field. So over Q, this would mean solving it over the p-adics. If you can solve it over the reals in the p-adics, you can solve it globally. So it's as good as it gets from a local to global principle. It's a celebrated theorem. It's not trivial. There are a number of different proofs. That's the easier half of the problem. The much more difficult problem was to solve it over the integers of a number field. And Siegel he developed many of his theories. He developed the theory, the orthogonal group, the symplectic group, the arithmetic theory, and most importantly, his Siegel mass formula, trying to solve problem B here. And he solved it in 5 or more variables. So if there are a number of variables, he proved this local to global. Once you go to integers, you have to allow finitely many exceptions if the quadratic form is definite, so that the number you're representing, there may be a few small numbers that are exceptions. So he did it in 5 or more variables. Kneser solved the case of 4 variables. The case of 3 variables actually requires ideas that are much more involved. There's no other proof that I know at this point. It actually involves quite subtle points in terms of modular forms, half-integral weight, subconvexity. A breakthrough was made by Duke and Ivanic, who solved the 3-variable case in this stable form over Q, and the general case of a number field here was solved by Cogdell, Piatetsky, Shapiro, and myself. The main reason that this is very different to what I want to talk about next, which is much more elementary, so this actually gets quite involved, is that if you are a sum of squares, f equals k is a sphere. It's a homogeneous space for the action of an orthogonal group. And in fact, one of the most important things is you can get all the solutions, or at least there are finitely many orbits, a feature I'll be looking for in this nonlinear next setting that I'm about to get to. If you look at the orthogonal group with entries in the integers that your problem is demanding, that will act on the solutions with finitely many orbits, so that the problem quickly becomes a problem about group theory and arithmetic groups and problems like the Ramanujan enter, and in particular modular forms. And these are all used to solve the most difficult case of n equals 3. So that's a case of linear and quadratic. And I have spent the last 10 years worrying about a cubic. So it's slowly moving up. Now, if you go to a cubic and you work over the rationals, you would be talking about an elliptic curve, if it were a curve. And that is shockingly rich. You'd think, why are the elliptic curves people working so hard on elliptic curves? It's beautifully rich. Many of the Birch-Swin and Dyer conjecture there, which is the main local to global statement, was born from Birch and Swinnerton and Dyer by trying to write down for a cubic over the rationals the analog of Siegel's mass formula. However, here I'm going to be concentrating on integer points on cubics. And so let me tell you what we know about that before we turn to the specific thing where we have some results. All right, so I have a cubic form. So I would like to just stick with homogeneous cubics. But since the whole theory that I'm going to describe to you where we make any progress at all is not homogeneous, I necessarily start off with a more general situation. So the cubic is going to be affine. It may not be homogeneous. The leading part must genuinely be of degree 3, otherwise things degenerate and become much simpler. And we ask the same questions that I was just asking. So it's just the case of the cubic where I discussed in the first 2 slides, the case of a linear and quadratic. And what I immediately will make the following notation, that K is admissible if there are no local obstructions, and as I said, that will always be easy to describe what the Ks that are admissible are. And they will be always off an arithmetic progression. Now, if we're going to have some method to produce integer solutions, well, it would be good if we have a lot of solutions. So if analysis is going to produce a solution, it's because maybe there are a lot of solutions. So I want to understand the richness of solutions. If there's only one solution, it's probably going to be very hard to find. But in these equations, when the case we'll be looking at, they may be very sparse. They may be, there'll be in the most basic cases, no methods to do these things. We may even go to a computer, as you'll see in a second. All right, so K is admissible if there's no local obstruction. It satisfies a Hasse principle if you have a local to global principle. And then you could ask, all right, if there is a solution, how rich are the solutions? Are there infinitely many solutions? Are the solutions sufficiently rich to be dense in the sense of no polynomials can distinguish them from the variety, in other words, being Zariski dense? And the strongest thing you could ask for is, are there enough solutions so that you give me any local solution, there's a global solution which reduces to that. And that's called strong approximation. So the best you could hope for is that you have a Hasse principle and you have strong approximation. All right, so we have a cubic form in n variables. Let's start with a subcritical case, which is the case where you can't expect anything. And that's because if I have a cubic form in two variables and I put f equals k, the theorem of Tour I mentioned yesterday I was selling Schmidt's work, which was this generalization of Tour-Siegel-Roth. The Tour theorem, and Siegel generalized it to curves, but this case is just Tour. F of x equals f of x1, x2, a cubic or higher, say, irreducible form, as we have it, equals k, has only finitely many solutions over the integers. So in that case, it's extremely unlikely that you'll have a Hasse principle. You still might have a Hasse principle that for each k you choose, one of those finitely many did the job. But that's not true. And in fact, Schmidt has a paper where he shows that amongst all, or you can deduce from it, that amongst all the k's up to k, the number of k's for which you have a Hasse principle in this kind of thing is, amongst the admissible k's, is much, much smaller. So there'd be only k to the 2/3 solutions, k to the 2/3 k's for which you have solutions, but even potentially have solutions, and for your typical k, the Hasse principle fails. So this is a situation, and I'll give you the heuristic of how you get to that point very easily in a second. At the other extreme, if I have many variables, so there is a method, it's called the Hardy-Littlewood circle method. It's been refined and refined, and the main aim in what people achieve in the Hardy-Littlewood circle method is to reduce the number of variables and still able to show that you have solutions. But of course, if you have many variables, f of x equals k probably has many solutions, so it's quite natural that you might even be able to show that you can count the number of solutions, and the number of solutions is extremely large, and hence not zero. That's how the circle method attacks the problem. So basically, the circle method involves writing down a Fourier integral which picks up the solutions, and then you study this Fourier integral around the circle very delicately at the rationals and at irrationals, and it's a rather robust method. And the best that we know in that direction is that if you have 10 or more variables, and f, the leading part of f is non-singular, then Browning and Heath-Brown proved that you have everything you want. In other words, you have strong approximation, you have Hasse principle, everything that's admissible is represented and handsomely represented. So when this analysis works, it works and gives you what you want. And then, of course, the question is, well, what's going to happen if I reduce the number of variables from 10 to 9, and then the techniques fail, but that doesn't mean the theorem's not true. And Hooley, actually, he passed away, I think, last year, but in one of his very last papers, actually proved something quite striking. It's conditional on two big conjectures, the Riemann hypothesis for Hasse-Weil functions whose analytic continuations are not even known. They should be, according to conjectures of modularity, but have an analytic continuation functional equation. But certainly the Riemann hypothesis is always going to be a very big assumption on this sort of thing. But these are problems if you solve this problem assuming those kind of conjectures which are in a different domain, to me, that's massive progress. So he got down to 4 variables, assuming that. If f is homogeneous and non-singular, then he proves not that every k, so in that case, some people might believe that every k is in fact represented, every admissible k is represented. There's no counterexample to that. But he showed almost every k is represented. Now, let me make clear here, almost every k doesn't mean all but finitely many k. I'm talking as an analyst. Almost every k means the number of k's up to k for which it fails is little o of k. But we can expect more there, but this is already a tremendous achievement. And it's really pushed down to 4, which is getting close to where you might still hope things are true. At 3, it's no longer true that you will always represent, that every admissible is represented. I'll give you counterexamples in a minute for various f's. But let me highlight one f that has been seeing the light of day on the internet a lot in the last 6 months. And that's, which numbers are sum of 3 cubes? By the way, I allow negative numbers. This is very important in my X's. So you can easily check, this has been known for many, many decades, that K, 4, and 5 mod 9 have no solutions. That's your local obstruction. So you're admissible if you're not 4 or 5 mod 9. And then there's a very beautiful question. Is every other number sum of 3 cubes? And mankind knows very little about this problem. It's as hard as any problem. Mordell, in his book on Diophantine equations, says this is harder than anything he's ever seen. It's possible that every number is a sum of 3 cubes, but we just don't have any tools to produce solutions or to... It may even be true that every one of these level sets is a risky dense. In fact, I believe that. It won't have the strongest form of strong approximation. I'll explain that in a second. In any event, there were a few numbers that, so people, you can go and try find small numbers, like you could represent 3 with 1, 1, 1. The numbers 33 and 42 had defied all efforts of people to find writing 33 as a sum of 3 cubes. And you can see there's a solution. I don't know if that's the smallest solution, found by Booker this year. That was sort of the breakthrough, and there's a number file on that. You don't go around searching there randomly. You'll never get the solution. You use a method, actually, that Elke's introduced, that he refined for this exact purpose, Andy Booker. And there's a solution. And we don't know any other solution with 33, if I'm correct. But afterwards, Drew Sutherland got involved in this too. So the number 42 is mystical to some people. So it's another number that was clearly a difficult one to find for a reason that I'm going to give you in a second. And they found this, and as you can see, the solution they find is rather large. I'm afraid that's more or less what I can say about sum of 3 cubes. So he's got a few more examples. We just don't have tools to tackle this kind of problem. But this is what happened when you went from squares to cubes. All right. There are 2 more theorems I wanted to mention. Lehmer and Boykers showed that if you take the case of writing 1 as a sum of 3 cubes, which you can by examples, but they actually showed that the set of solutions is a risky dense by a very clever argument using Pell's equation that was then generalized by Boykers, or made more geometric by Boykers. So it's the only case, and of course, not just 1, but maybe a cube. But there are very special Ks for which we know there are infinitely many solutions. So like this case of 42, that's one solution they have found. I don't know if there are any more. My personal belief is there are many more solutions, and that it's pretty rich. There is one breakthrough. It's a short paper of Castle's, which was then pursued further by Heath-Brown and made into a quite beautiful theory by Colliot-Thelen and Wittenberg. They were trying to find some algebraic reason or some way that maybe some k is not a sum of 3 cubes for other deeper reasons than just being not locally solvable. And there's something called a Brouwer-Manin obstruction. I won't go into it, but Colliot-Thelen modified the definition to have an integral Brouwer-Manin obstruction, which is quite sensitive. And using that, I'll give you one example of what this thing can do, is that this was already Castle's observation, that if you want to write 3 as a sum of 3 cubes, you can write it as 1, 1, 1, and there's another solution that was recently found by them. But whatever the solutions are, there's a non-obvious congruence that has to be satisfied that is coming from cubic reciprocity. That was Castle's observation. This is a Brouwer-Mannion obstruction, that any solution to writing 3 as a sum of 3 cubes must have x1 congruent to x2 congruent to x3 modulo 9. And that's not forced on you from the equation from local considerations. And that's a much deeper thing. It's a reciprocity. And for each k, there is a progression that's omitted. And these numbers, 42 and 33, the reason they were hard to find those solutions is there's the congruence based on them makes them much rarer. OK, so in terms of cubes, some cubic forms, there is one cubic form that's very well understood historically. It's one of my favorite theorems called the Dirichlet unit theorem. If you take a norm form, it's a cubic form in 3 variables, which is norm from a cubic field down to Q. Those guys you factor into linear factors, and they're cubic forms for which you can understand which numbers are represented. And that's the algebraic number theory. But that's very structured, and it's a torus, and it's one we understand. So what I want to explain here is a theory that I started working with Gumbert and Bergen years ago, and recently with Gauche, which is a cubic form which comes from Markov surfaces and is quite rich, and for which I would say we have the beginnings of a Diophantine theory. And the point is that we're going to have symmetries on these surfaces, and we're going to use these symmetries to the hilt to say something non-trivial. So I'm going to change a cubic form to this cubic form. So this will be the Markov cubic surface, and at the end I'll tell you the general context of these kind of equations, where I think they're exotic and they have the feature of having something like homogeneous spaces, but they're not homogeneous. All right, so the form is the sum of 3 squares minus the product of 3 numbers. That's a cubic form, and I want to understand m equals k. So the form, instead of being the cubic form, sum of 3 cubes, it's this form. The case k equals 0 is called the Markov surface. I'll tell you more about it in a minute. The case k equals 4, if you homogenize it, is the famous Cayley cubic. The actual solutions of this equation, especially the Markov case, comes up in a number of different areas in mathematics, which is another reason that I found this to be a very beautiful case. Firstly, Markov himself was interested in this equation because it gave you the Markov spectrum in Diophantine approximation. The integer solutions in the case when k is 0 of that equation, so m equals 0, allow you to read off on what's called the Markov tree the best approximations, the worst approximations to numbers by rational numbers. It's called the Markov spectrum. The simple closed geodesics on a subgroup of the modular group are in 1-1 correspondence with the Markov solutions to the Markov equation. This was observed by Harvey Cohn many years ago and is a viewpoint that's very important to us. There are problems in algebraic geometry whose solutions, the solutions are projective spaces with certain weights, and the weights are solutions of the Markov equation. Aru showed me a couple of years ago when he was at the Institute visiting for the year an invariant in Lefschetz fibrations, which he was able to use the Markov equation to distinguish various fibrations. So it seems this is a very natural equation, but perhaps the most important viewpoint for us in this lecture will be that the affine equation, m equals k, is the relative character variety, which you look at all representations of the fundamental group of a torus, once punctured torus, into SL2, into 2x2 matrices. You look at all those representations, and you divide out by conjugation. So you compute the character variety of this. So I look at the representation space and identify 2 if they are conjugate. That's a character variety. And that, in this particular case, goes back to Fricker, is this m equals k, the relative character variety. And there's a natural group that acts on this character variety, which is the mapping class group, more generally also. And the interesting thing is everything has an integer structure here, and the group is acting as preserving integers, as I will do now in this very explicit example. So we have a situation where we actually have some extra ability to make new solutions from old solutions by some nonlinear transformations. The connection with Payne-Lavey 6 I mentioned yesterday, and I'll return to because I owe you a proof there. All right, so since I'm assuming that you haven't seen this every day, let me remind you what these might look like. So the Markov surface was m equals 0, k equals 0 in this picture, and there's a solution 0, 0, 0 in the middle, and then you've got 4 components there. This is the real solutions. That's what they look like in real space, in affine real space. If you move k from 0 to 4, what happens is that little blob, the origin grows into a little compact piece there for the surface. And then when k is 4, at the Cayley case, this is the unique case where you have these 4 cone singularities, and that's why the Cayley surface is so important. When they join, and when k is bigger, you already have one component here. So that's what the real solutions look like, and we're interested in the integer solutions on there. Okay, and the reason that I said to you that in the quadratic case, the space is homogeneous, and the whole theory of quadratic forms can be, that aspect of the theory can be generalized to homogeneous varieties for linear algebraic groups where you have the GZ acting on VZ with finitely many orbits, but acting linearly. The interesting thing here is that the action is nonlinear. So in this situation, we have the integer solutions. I don't know if there are any solutions, but if there is a solution, the following group acts on the solutions to produce potentially other solutions. So here is this affine action, which I'm going to call the Markov group, or you can call it the mapping class group. It is the same in that example. I'll call it gamma, and it's mappings of 3 space to 3 space generated by the it's finitely generated this group, generated by the following 3 involutions and permutations. So the 3 involutions are R3, there's the one I'm writing down there, is you fix x1 and x2, and you replace x3 by x1, x2 minus x3. Where's that coming from? If you look back at this equation, if I fix x1 and x2, then in x3 this equation is quadratic, and that's just flipping the roots. So if one of the solutions is an integer, the other guy is going to be a solution, is an integer, and so you could easily compute exactly what it does, and it's this transformation. If you apply it twice, you'll get back the identity. But if you apply R1 and R3, you'll get something which is more complicated, and it fixes x2. And then if you take the group generated by R1, R2, or 3, you'll get a highly complicated nonlinear morphism group acting on 3 space. No, I mean R1, R2, or 3. You're correct. You are correct. Absolutely. As an abstract group, this group is isomorphic to PGL2Z, but it's not acting the way PGL2Z acts here, so that's a red herring. The case of the Cayley cubic, k equals 4, is everything I say is false. It's a singular case. It's sort of the case where things are acting linearly secretly in some other coordinates. So I'll ignore that case. And this, in more generally, there will be some singular cases like that. What Markov did, and then Mordell and Hurwitz, or Hurwitz and then Mordell, was to observe that these take integer points to integer points, and in general, for any k, this action has a descent. You think of this group as taking a point, and you can make it somehow simpler and bring it into a bounded region, and there are only finitely many orbits. So if there are any solutions in the first place, they're only going to be finitely many orbits. And that feature is this very similar to the linear case, which is a highly non-trivial theorem that in general the integer points of the group act on any affine homogeneous space with finitely many orbits. This is true in this nonlinear setting by a descent argument. which is due to Markov. Okay, so the basic classical questions in this that have been studied since Markov and Frobenius are, when is this non-empty? So for which k is this non-empty? Or saying, when is this class number? I'll just call it a class number. It's just the number of orbits. There's no class group here. When is this class number positive? If it's infinite, is it Zariski dense? Now we have a very good feel that if there's one point, we can make new points. So we probably are in a situation where we might be Zariski dense. And is it possible that for a cubic, you have strong approximation? I should have said why the threshold was 3. This is the Hardy-Littlewood argument of how you do these things. So if f is degree m, and I take the variable, and I'm in n variables, if I look at the x's up to size t, I will get, if I have n variables, t to the n numbers. But the f, the values it's taking in the integers would only be, if the degree is m, t to the m. So I'm putting t to the m numbers in t to the n boxes, and maybe they're just sort of placing themselves randomly, except for these congruence obstructions. So if n equals m, I'm going to more or less hit each guy a bounded number of times. If if the number of variables is bigger than n, I should be hitting a positive power number of times. And that's why we might believe that if you're a cubic form and you have 4 variables already, you probably are in good shape. And if if you're fewer, you don't have enough balls, that's the Siegel case that you, of course, have no chance of being able to have a Hasse principle. So that's the heuristics, and they all measuring out, and we in this critical situation. All right, so when does this happen? And that's roughly what we're going to try to answer here. So the local congruence obstructions are easily computed. The situation, like in the sum of 3 cubes, is you better not be 3 mod 4 or plus minus 3 mod 9. I told you that's easy. It's because it's just a question of counting the number of solutions mod p to these equations, which is straightforward. They're not complicated varieties. And we're looking for ones which are the VKs which obey Hasse. So we'll only stick to admissible Ks. And I want to explain something that Gauche found that I was completely blown away by. Most of you have seen these pictures of a fundamental domain for the modular group. That's on all the posters of most conferences. That's Gauss reduction. He worked out that if you have a binary quadratic form, positive definite, the action of change a variable on that, which is similar to this situation, but it's a linear action, can be brought into this fundamental domain, which is some condition on A, B, C, and then you can tell whether 2 forms are equivalent from that, so it's algorithmically very nice. Here we have a nonlinear action. I told you we have a method of doing some kind of reduction. But to my surprise, when Gauche started to look at this to try to see if there's what these sets look like, he found a fundamental domain for this nonlinear action, which is as pretty as Gauss, maybe even prettier. So here's Gauche's reduction. So firstly, we'll assume k is greater than or equal to 5. For k smaller, you can look at it just directly. And then I'm going to remove all solutions where one of the coordinates is 0, 1, minus 1, 2, or minus 2. If any one of the coordinates is that, then the k that's in question will be a quadratic equation, and you can analyze them separately if there happens to be a situation like that. That's important that you have to remove that. I'll explain that in terms of the dynamics later. But you remove those, and then his theorem is, say for k positive, that the set of a point is, I'll call Gauche reduced, meaning that you use this group to bring it into the following position. So if k is positive, I'll write the coordinates of the solution as minus x1, x2, x3, and I just order them, x1 greater than or equal to 3, less than or equal to x2, less than or equal to x3, just in this cone. And of course, it must satisfy the equation. That cone condition means that you have only finitely many solutions, but that's just that simple linear condition. And the claim is that there's exactly one and only one point of each orbit inside that set. So if you want to compute hk, you just need to compute how many points there are in that set. And this opened the door for us in order to see. We had no idea. We started out thinking, well, this is as hard as the sum of 3 cubes. to a... Sorry, what? I think it's correct. Oh, it should be, it's got a minus there, yeah. Okay, it's correct. All right, already from that, and this is absolutely critical for the main theorem that I'm about to tell you about in our work, is once you know that there's one solution in this set, which is just a cone like this, then if I want to count how many, if I want to compute the average value of this class number hk, it's just going to be a volume consideration because the number of points inside this region with k less than or equal to k will just be the mean value. So the next theorem is just immediately consequence of his reduction. In fact, both A and B are immediate consequence. Firstly, these class numbers, which were finite, are at most k to the 1/3. And then the mean value of hk, and this is the key point, it's not k. I told you that these things are putting balls in boxes, but actually there's an extra log k squared. The entire theorem is dependent on noting that. So it turns out that when you're counting these points in this particular region of his, you're going to put these balls in boxes, but you're going to put more and more, the average number of balls is going to grow slowly with k. If I'm going to be trying to say eventually that the Hasse principle is true for almost all k, that's better be happening or I wouldn't have any freedom to make that gain. So that was critical. So the mean value is log k squared, both in the negative and the positive. He went and ran the computer for a long time and came back with a very clear answer of what's going on, not that you can prove this, and that is that the Hasse principle fails for k to some power time. So it's not true. Quite simply, with sum of 3 cubes, we know of no Hasse failure. Here, the Hasse failure seems to be persisting. It's failing for k to some power, roughly 0.9, numerically. And that sort of gave us our marching orders. It seems that this is a critical situation where there are many k's for which you have a Hasse failure, but not most k's obey the Hasse principle. If we knew that, I don't know what's true for sum of 3 cubes, but it might be similar. Actually, at the end, I'll say I don't think so. The minute you put structure, you can make progress, and you're not your typical situation. Your typical situation you can't touch because you don't have anything to tackle, to attack it with. Yeah. That they satisfy the equation. It's just like Gauss. Gauss has B less than or equal to, this is when K is positive. Just put you in a compact set. Yeah, minus X1. Yeah, that's what he was confused. Sorry. Okay, it's probably poorly written. Yeah, there's an example of his thing in action. All right, so now let me state the main theorem. Given what we saw numerically, this is what we were able to prove. There are, in fact, infinitely many Hasse failures. The number we can produce is about square root of k, slightly less. For each t, the number t greater or equal to 0, the number of k less than or equal to k with k admissible, we only stick to admissible, for which h of k is t is little o of k. So if you ask how many k's are less than or equal to k for which h of k is 0, which means that Hasse fails, then it's true for almost, Hasse's failure, then it's true for little o of k of them. So almost all k satisfy the Hasse principle. That's what we were seeing numerically. The only thing that we not picking up here is that exponent k to the 0.9. We're getting k square root, we're getting only square root k. And that's because we found a way to produce Hasse failures. And that came from a reciprocity, so I won't go into it. We found a technique using quadratic reciprocity and multiplicativity to produce about square root of k numbers up to k, which fail Hasse. We also, part of that construction also incorporated the descent, which is using this Markov group. So those are constructed explicitly, and they're only square root of k. Numerically, there are many, many more that fail the Hasse principle. I can't explain that. That seems to be what's happening. This is how many we can do. This was begging, and Kolyot-Thelen immediately responded that surely his invariant, his Brouwer-Mannion obstruction, must be explaining what we're seeing. And indeed, he computed the Brouwer group here, 2 separate groups, and they found that half of what we were producing were explained by the Brouwer-Mannion obstruction, but the other half not. And that's because the other half combined this argument with the descent. And the Brouwer-Mannion obstruction doesn't know about descent. If they build in the descent, then they're explaining all our cases. The advantage of his point of view is he's got this Brouwer group, and he can say, this is all I can explain. Well, what we're doing is we're just saying, all right, here's an ad hoc argument. He's limiting what he can do, which is always good because it means they understand what they're doing. But from his point of view, there are only square root of k Hesse violations that are explained by algebraic Brouwer-Mannion type obstruction. But I emphasize there are apparently numerically many more. Let me just emphasize that for a sum of 3 cubes, I don't even have a decision procedure. If you ask, is some number a sum of 3 cubes, and you search and search and you don't find anything, I don't know how you convince yourself, well, actually there aren't any solutions. This descent is what allows us to decide for each k whether you are represented by this Markov cubic form. So those are the examples. I want to say a word about the proof, because I mentioned Hooley, who had done 4 variables, and here we're in 3 variables. Why are we succeeding unconditionally? And this part doesn't use the descent group, but it does use the structure. So it took us a while to find the right formulation, but the way you prove that almost all, so I'm now explaining the idea behind the proof that almost all k's satisfy Hesse. So for almost all k's, I want to see there's a solution. In fact, for almost all k's, they're going to be about log k solutions. That's where that log is so important. If that were bounded, this technique wouldn't work. So what we do is, and this is motivated by the Siegel mass formula and by BSD and something like that, and it's a technique probably worth keeping in mind if any of you ever face something like this. So you're trying to count the number of solutions equals k by m. You don't know what the answer is. The best guess that you should ever put there is to put the product of local masses. So you force the product of local masses. You compute how many solutions you expect to see there by multiplying the density of solutions at each prime and at infinity. And that's an analytic expression which comes from local. Anything coming from local ideas you can compute. You put that there, you take how many solutions you really have, you take the difference, you square it, and you average it, and you try to show that goes to 0. That will mean that for almost all, it is the local prediction. The fact that there has failures means that this is wrong for a lot of the guys, but I'm only trying to prove it's right for most of the guys. And then there's a separate argument that the local product is giving you a non-zero answer, so that on almost all, it's giving you an answer which is positive. The fact that the product of the local guys is not 0 is some, again, product local things. And it, of course, picks up the admissible feature right there, because that product would be 0 if there was a congruence obstruction. All right, that's the mechanism of how you proceed. How do you execute it here? We have a method where, because this is the second structure of this form that we use, because the form is a sum of squares and the cubic term is appearing with each term linearly, we fixed, so when you square that out, you get a form in 6 variables, because you're computing a variance, and you fix 2 of the variables, which are small, and they are giving this log behavior, and then the other 2 variables are now a quadratic form. And the minute I'm with a quadratic form, I throw in all the machinery that I was mentioning to you before that we understand so well. So you have to understand how many ways you can solve a quadratic equation with variable coefficients in regions that are changing. But the bottom line is we understand quadratic well enough, and that opens the door and is the central feature in that proof. I'm running a bit slow here. I was going to give you the proof of yesterday. So I'll still skip it. Sorry. I was going to give you the proof of Lang's gem implies, but I want to get to some other things here that are interesting. All right, how about strong approximation? So strong approximation is, once we have a point, we now can use the group to produce many points. They'll be Zariski dense. That's not hard to show. And the question is, maybe they satisfy strong approximation. are there enough points that when I reduce, I get everybody? And this becomes a question about the action of the mapping class group acting as a permutation group, which is a beautiful problem which we haven't solved completely. This is the joint work with Gumbert and Bergen that we partially solved, but enough to do quite a few things. So let me stick just to the Markov case where k is 0, and I'll change the coefficient in front of the cubes to 3, because then it's exactly Markov's equation. That's not important. So the R3 and R1, R2 are slightly different. And Markov's theorem in this exact equation is that the class number is 2. There's one solution, which is 0, 0, 0, and then there's only one other orbit. That's the basis of his tree. And so let me look at the solutions and see how they reduce. Since there's only one orbit, I can take this group and I can see how this group acts on the solutions mod P. So I look at the solutions to the equations mod P. The Markov group, which is these affine transformations, now works on everything mod P. That's immediate. And it's acting as a permutation, acting as permutations on the solution set. They're about P squared solutions to this equation. And the question is this permutation, is this action of the mapping class group or Markov group mod P, is it transitive? Because that's what will give me strong approximation. Because I only have one orbit. Globally, I have to start from 1 and I get all the solutions. So if I'm going to reduce and get all the solutions, it better be that from 1 I can get to any solution. So this action needs to be transitive. So this seems to be a very difficult problem. How do you study the action on the solution set here? I will end by explaining that a better way of formulating these things in terms of actions and relation maybe to people who've worked with the mapping class group. But we just took the low road here. We just decided, okay, we're going to try to prove this acts transitively, and we were essentially able to prove it, but not quite. That is, the set of P's for which we can prove the conjecture that this action is transitive is large. In other words, look at theorem 3 here. The set of primes less than T for which the strong approximation conjecture, which is this statement that this permutation action is transitive, the set of primes for which it fails is at most T to the epsilon. So unfortunately, and I don't want to go into the proof here, but we really thought we could push this through, and now I think a fundamental new idea is needed, so we can only get it in this form. The conjecture should be then, once P is large, this is transitive. All we can prove is once, forget about P is large, the number of failures, which is supposed to be empty, is at most T to the epsilon. And we could get down to log there. And that the proof produces a big, fat, giant orbit. The point is you're trying to prove this action is transitive. You want to show that there's just one orbit, mod P. What we show is there's a giant orbit, and then the other orbits, which have to be very small according to that estimate that we do have for every P, the other orbits, they have to be small, but they have to grow at least like log. So what's really happening there is there should be just one orbit. In general, for arbitrary P, that's all we know. But for P, when we prove this theorem where there may be many exceptions, but not too many exceptions, in that situation, we show that these small pieces that might not be connected to the giant component are actually all connected. And I'll say a word about that. That has got a nice proof. Possible there's something much simpler to do this. It's quite natural that once you have a permutation group acting on the set, you could ask, what is the permutation group? Right? It's acting transitively. Is it as big as it could be? And Puda and Mary showed that if the group's acting transitively and P is 1 mod 4, they can't do P 3 mod 4, that's still out of sight, then the permutation group is as big as it could be. It's either the alternating group or the symmetric group, and you can decide which by just looking at the generators. So that's a much stronger statement. Not only is the group acting transitively on the solutions, but it's actually as big as it could be. There's a very good reason that that's useful. There's a lemma that I learned from Katz, which is called the Gaussat lemma, which tells you if you have a subgroup of the product of two groups, and suppose it projects onto each of these groups, and you want to know for free that it is actually the whole product group. Well, if G1 and if the groups are abelian and they have no common factor, then that follows. And in the non-abelian setting, if they have no composition factors in common, then it has to be onto. So you can get the action to be transitive on the product of two groups for free if you know something about the automorphism groups and that they have no composition factors. And so what Puda and Mehri have done there is they've opened the door for us to do this because we had another proof of this, but this is infinitely better. Infinitely better, because now if I take the alternating group with one P and another P, they have no composition factors in common, so you fall free onto the product in this situation. And why am I so eager to know that I'm free onto the product is if I want to do any kind of number theory and I don't know what is happening mod Q for my solutions, how can I do anything like sieving or anything further? And this opens that door, and it allows us to prove theorems about Markov numbers, which I think I've spoken about before here some years ago. So I'm going to, there was, Bergan, Gumbert, and I were able to answer some questions of Frobenius about what Markov numbers are modulo P. We still have this weakness that we don't know all P, but it was enough to do a sieve and even use some work of Mirzakhani to show almost all Markov numbers are composite. Sounds greatly disappointing when you would much rather say there's infinitely many prime Markov numbers, but these problems are so hard, they're Lachenry problems, that's, by our standards, considered to be, or by, we feel it's quite an achievement. I want to say one word and then talk about the generality, which I think is more important where the subject, I hope, is going. So let me say one word about the proof of the fact that this action is transitive. At some point, you're doing combinatorics, and you do what I said you do. You have this giant component. You're now trying to join each little guy to the giant component. And the important thing is you start with your small component, and you make some rotations and try to show they connected to something that's a little bigger. And then, in that case, you get to count the number of solutions to an equation over a finite field. And if you can make that bigger and then you iterate that, you eventually have to be swallowed by the big component. That's roughly how the argument goes, but there's a finite field thing that intervenes that is very instructive. And it's the following. Suppose I'm in the finite field Fp, and I have the equation y plus y inverse equals x plus lambda x inverse. Everything is in Fp. And I'm trying to solve for x and y. So if I was just trying to solve for x and y freely, that would be a curve, a very simple curve of a finite field. There'd be basically p solutions. But I want x and y to be in subgroups of the multiplicative group of Fp. Okay, so H1 and H2 are multiplicative subgroups of Fp. Their sizes will depend on p minus 1. Suppose the size of H1 is less than the size of H2. And I want to give an upper bound for the number of solutions to this equation in x and y. Well, the trivial upper bound is if I have H2, there are at most H2 solutions for y, and then x there's at most 2 solutions. So it's basically H2, the bigger one. That's a trivial bound. But in order to make this iteration process that I described, starting from the small set to get to the big set, work, we need to give an upper bound for the number of solutions to this, which is the bigger subgroup to a power delta less than 1. That's the key. And this sounds like maybe the Riemann hypothesis for curves over finite fields will do this. And it does if the size of H2 is bigger than root p. The point about the Riemann hypothesis for curves over finite field is it gives you the number of solutions is p plus 1 plus square root p times the genus. If the genus is bigger than root p, that's not very useful information. So as long as the genus were large, and that means in this case here that the size of H2 is bigger than root p, you could just use Weis' theorem. But if the set is very small, which we have to start with a small set and join, then that's not good enough. And I make this point because I think it's an important point. You have to go to the proof of the Riemann hypothesis and see if there's one of the proofs are better than other proofs to still give you something non-trivial here. And there's a proof by Stepanov, an elementary proof of the Riemann hypothesis for curves over finite fields, which gives enough information in this case when the genus is much bigger, and is exactly what we need to complete the argument. So it's a point that the world doesn't end with the Riemann hypothesis. There's more to it. Maybe the proofs are more important. All right, the setting in which, I have 5 minutes, the setting in which this can be generalized. There are a few settings, but one I think is immediately suggested, since I said the way we might think of this is the once punctured torus and the character variety is to take surfaces of genus G with n punctures in general and look at representations of the fundamental group into SL2. And the interesting thing is the character variety that we've been looking at here, which was that equation, is still defined over Z. This goes back to Fricke and Klein. The set of equations you can write down in this affine model is actually integral. So there's a whole Diophantine theory of character varieties, because they're defined over Z, for which you will have the mapping class group acting on integer solutions and taking integer solutions to integer solutions with this miraculous action, which is what gave us all the mileage. And for those, it's then natural to ask if these are kind of exotic or threshold varieties for integer points on varieties, because we have this extra action. And Peter, well, I call him Peter Wang here, who got his PhD in 2018 and is here at MIT, so any of you are welcome to talk to him. I'm sure he'll be happy to explain much more than what I'll say here. Has started looking at the basic questions here in this generality. So the first question is, are we in a situation where Voigt's conjecture should say that we are a threshold situation? And the answer is yes. This relative character variety, he proves, is log Calabi-Yau. That's exactly the condition for being on the threshold, where if you were if the canonical class were slightly more positive, there would be no solution. According to Voigt, you wouldn't be Zariski dense, possibly Zariski dense. And in the other direction, I think people don't know, but they might say, all right, maybe there are many integer solutions. So that was like cubic form in 3 variables. So for G equals 1, n equals 1, this was something I explained in low-brow terms, but this is the right setting in terms of the complex geometry of the affine character variety. The second thing is developed a descent theory, which is not at all like Markov's here, that shows that, this is a bit of an exaggeration, but I think it's fine, to say that this nonlinear group acts with finitely many orbits. There's some condition about, like when some special points, which I don't want to go into. But essentially, we are in the same position that we have this group acting and taking integer points to integer points with finitely many orbits. So we're in a position where we can now try to tackle the Diophantine analysis of integer points on this. So this is one direction where you can clearly want to try to repeat some of the theorems that are proven before. And let me state 1 or 2 such problems that are still, I think, are fundamental. In the case of the real points, so if I take this character variety and I look at the real points, Thurston and later Goldman and other people have studied the action of the mapping class group on the real points, on all the components Goldman did. Thurston studied it mainly on what's called the Teichmuller component. He might have studied more generally, but what I've heard of is on the Teichmuller component. And on the complex points, there's beautiful work of Cantat and McMullen, where they actually look often at one element and try to understand its entropy, but they also look at the whole group. So these things, the action of gamma on the real points and the complex points are obviously very relevant to us. But the interesting thing here, what this has brought out, because we defined over Z, is you can look at the p-adic points. And what is the action of gamma on the p-adic points? There's some very basic questions here. There's something very different with the p-adics. In the reals, this action, say on the Teichmuller component, is discontinuous, and it's not compact, and then Thurston's theory is taking place on the boundary. In the p-adics, the p-adic integers are preserved. These things preserve integers, so they will preserve the p-adic integers. So xkzp is now a compact invariant subset. And what the work of Gumbert, Bergain, and myself does, and Puda and so on, is that it shows that this action seems to be minimal on this compact part, meaning the closure of any orbit is as big as it can possibly be. The topological closure, topological closure is wanting to be as big as it can be. I think this is the way to think of this. This mapping closed group is acting on the p-adic integers in maximally. I think that needs to be understood and proved. And maybe if you understand it this way, you'll be able to avoid our lowbrow arguments. There's a question of what the finite orbits are. Well, obviously, if I'm going to say the action is as big as it can be, you better first find the finite orbits, which I made a big deal about last lecture, and I said it was connected with Paine-Lavey. Well, what are the finite orbits in this generality? And Biswas, Gupta, MJ, don't know how to pronounce it, and Wang, very recently classified the finite orbits, at least if the genus is greater or equal to 1 and n is greater or equal to 0. So you have this character variety, and there's an obvious way that you'll have a finite orbit, is if the image upstairs of your representation is finite. And basically they're saying is that the only finite orbits, except for cases that you analyze separately and explicitly, are ones which come down from finite images. I think you asked a question along these lines. So that's quite nice. It does not contain, does not give a new proof. Their proof does not use Lang's GM, but it does not give a new proof of the Paine-Lavey 6, because that case is the 4-punctured sphere. So the Diophantine analysis there is still, I think, critical.
Can I just ask, like in general, there's always the case with the image of a representation is like in some subgroup.
Yeah. So in general, you would, right, it would be, of course. You might lie in a subgroup, right?
So when you say
I said essential. I said, yeah. It's a vague question. In general, I'm just trying to say that you first have to recognize where you lie, and then I can formulate for you, and then whatever you recognize is where you should be. But it's probably much more complicated than I think. All right. Now I must make, if you give me 2 minutes, I must make one very important point here. If you change the numbering from Z to Z adjoin 1/5, so that they're infinitely many units, or you change it to Z root 2, then, sadly, this group is no longer acting with finitely many orbits. This was first observed by Joe Silverman in the case of the Markov equation. And it's a general fact. And so all of a sudden, the great mileage you had disappears. So this kind of thing that these symmetries are just beautiful and they're moving around seems to be just connected with the integers. But still, you've got a lot of mileage here, and we've been working on this, me and some other people, because there's some beautiful, challenging problems here, and I want to end with a problem that I put out for all of you, elementary problem that I think is beautiful, and we have some connection to that problem when you're looking at SL2D, where D is a ring of integers, which is like above there, which has units, which, because of this, by a theorem of Serre, satisfies the congruent subgroup property. So here's an equation which is very close to these equations, and I'll leave you with this. A question of Aner Shalev, it's a beautiful question. Is every element in SL3Z a 1 commutator? Can you solve the following equation, x inverse y inverse equals b for any b in SL3Z? Let me make clear there's no local obstruction. So Shalev and these other fellows have proved the following, that there's no local obstruction. In other words, there's no finite quotient of the group in which that fails, which would be enough to show that. So the analog. Now, the reason that you can answer such a question for all finite quotients is the congruent subgroup property. All finite quotients of SL3Z are congruence quotients. So they're checking number theoretically that there's no obstruction. And this problem is very close. I can't even tell whether it's true or false. It's very much like a sum of 3 cubes. It's at the edge there. One day you can think it's true, one day it's false. Nothing is known about it. Even how to check. There's no algorithm that I know of. If I give you a B, that'll work for every B, whether it's a 1 commutator. So I leave you with a group theory Diophantine problem of that nature. And the case of SL2D, where D is a ring of integers with units, is very similar to that, closely connected to the Markov equation, and I think we hope to say something non-trivial there. Well, thank you for listening to me. Sorry for going over time. Yeah, it's Friday. Even I was falling asleep. Yes.
Maybe this relates to what you're saying about if you look at
Yes, so we've studied that. Yeah, yeah. Okay, I was going very fast here. There's a theorem. Yeah, that's a very, so I do understand it in that case. Sorry. It's this question here. There. Under the same assumption on P, the orbit of every point in Y star, that's where at least one of the coordinates is not 0 modulo P to a power, then the orbit is full. What do you mean by permutations? Yes. Right. Oh, what's the group? Yeah. Okay. It's some Reith. Okay, I don't. It's some Reith product. Yeah. When you go to the limits, the Reith product is quite complicated. Right. You have to take that into account. Yeah. They know it in this case of P congruent to 114. So for the Markov case, I think we do understand this feature, what the answer is basically. I think that's probably the most clear way to formulate this action because people have studied the real and complex. It's clearly a p-adic question being asked. Yeah. What's the action of the mapping class group on the p-adic solutions? Yeah. Sorry, so it's transitive anyway. Yeah. Oh, thank you. Made my day. Thank you.